Hello everybody. These are video notes on electrical circuits. I am going to show you a new language in these sets of notes, and it's the language of electricity. It's very important to realize that electricity has to go in a complete circle or a loop or a circuit, kind of like a traditional roller coaster, where you start in the train station, you go up a hill, you go through the entire ride, and then you come back in the train station. If there's any part of the circuit that's missing, that train isn't coming back to the station, and in electricity, that electricity isn't going to go through the loop, through the circuit. So I'm going to show you a new language, and as with all languages, we have to have our letters. So I'm first going to show you some of our letters in electrical circuits. If we ever draw just a simple line, that line is a wire. And a wire is anything that will conduct electricity. Metal being the big one. Copper being the most common metal that will do a good job of conducting electricity. So if we draw a line, we are drawing a wire. Doesn't even matter how long that wire is. What I just drew here on my screen could be 2 centimeters, so it could be that long, or that could be around the earth 2 times. Wire is wire, doesn't even matter how long. Next thing I want to show, I'm actually going to show you twice. We will always draw it like this so we can see where it is, but to just show the difference between these two things, I'm going to draw them slightly differently. These are both switches. So that's a switch, and this is a switch. Well, we call this one an open switch. This one is called a closed switch. But when we draw switches, we draw them open so we can see where they are. It's a lot easier to see this switch than this one. If you don't see that that's lifted and there's a little circle there, you might just think that this is a wire. So we open all of our switches just to simply show that it's there, but this can then move down and it's now a closed switch. Electricians talk about switches being open or closed, but commoners, people who aren't electricians, talk about switches being on or off. Well, in most situations, an open switch is going to turn something off, and a closed switch is going to turn something on. Going back to my roller coaster analogy, if this open switch is a roller coaster track, that train is not coming back to the station, and therefore they're not even going to send a train from the train station if they know that there's a big gapping hole in the track. But if that switch is closed, meaning that entire wire is connected, now you got a complete circuit, and that wire or that switch is on, also known as closed, because it can go through the entire circuit. So those are switches, and I'll show you switches in class. The next thing I want to show you is this kind of ugly thing, but think about what it might be. Sometimes you will see people draw this. Let me draw another one right here. Sometimes people will simply draw it like this. So these are 2 examples of the same thing. That doesn't tell me anything, even though I now know what it means, but that to me actually kind of looks like a light bulb. That looks like an incandescent light bulb, the traditional old style light bulb. Well, we can put any kind of thing that uses energy. We could put a heater there, we could put a speaker there. Anything that converts electricity into the stuff we use could be our energy, what's using our energy. The only thing we're ever going to use in class is a light bulb. So that's how I will draw light bulbs. If you want to use an X because it's easier to draw, that's fine with me. Last thing that I'll draw a couple different ways. We'll just draw it like that. This is how we draw a battery. And I'm going to give you a worksheet, and they refer to a battery as a cell. The reason is how many cells do I have up here right now? The answer is 1, 2, 3, 4, 5, 6. This is 6 cells, or 6 batteries. Example, the reason we do that is because we can put batteries back to back. If these were both D batteries, I grabbed a C and a D, but this is the reason batteries are put in appliances in opposite directions. If you put 2 batteries like this, there's wiring in here that's getting it into a circuit, taking it through, let's say, your remote control. But that's why we put batteries like this. So this would be 2 cells. And I grabbed some 9-volt batteries. We know what these little square batteries look like. Well, if I take 2 of them and connect them, I now have an 18-volt battery. If I connect 3 of them like this, and notice we still have the little tab and the big tab to connect stuff to, I now have a 27-volt battery. And that's how batteries and wall outlets and everything we do is going to be with batteries. Please do not mess with an electrical outlet in a wall. Those are carrying 120 volts, anywhere between 15 and 20 amps. Amps are what kill people. Current is what kills people. So please don't mess with a wall outlet. We will mess with batteries. But as a real quick lesson, this is a AAA battery, 1.5 volts. This is a AA battery, 1.5 volts. This is a C battery, 1.5 volts. This is a D battery, 1.5 volts. Why are they all different, or why are they the same volts but different sizes? Because this isn't going to fit in your remote control very well. This isn't going to fit into an MP3 player very well. But these will fit into your remote control and your MP3 player just fine. So if you have something big, and the difference, besides size, this one's going to last longer. This little AAA isn't going to last as long. But this ought to last quite a while. The battery you're going to see most in class as we start our shoebox project, this is actually a 6-volt battery. This is a 9, and I just showed you all these ones that are 1.5. Well, these will last for a long time. You can find these in the camping section of most stores. So that is everything about drawing a circuit. That's everything about drawing a circuit. But now, let's draw some circuits. There are 2 main kinds of circuits. The 2 main kinds of circuits are a series circuit. In a series circuit, everything is in one loop. So I'm going to draw 4 cells and 3 lights and 1 switch in a series. So 4 cells, 4 batteries. There's 3, there's 4. Now let's put a switch in here. Then let's put 3 lights in. There's a light. And notice, all of the circuits I draw are going to be a box. Please draw boxes when you draw. Oops, let's back that up. Please draw boxes. Yeah, we keep saying circuit, which means circle, but boxes are still going to come back to their original location. Now look at this. I got 4 batteries hooked to a switch, hooked to 3 lights. What is going to happen when that switch is open? Can electricity make it from the battery back to the battery? Can it make it through our loop? Think about it as a roller coaster. If that switch is open, is that train going to make it across here and come back? No, it's going to go off the tracks because the track is missing. But if that switch is closed, what's it going to do? It's going to make it. If the electricity goes through a light, the light is on. So this switch is going to control all of these lights. And we will build series circuits with 1, 2, and 3 lights. Then the other kind of circuit is called a parallel circuit. And this is what makes all this stuff fun and interesting, also known as complicated. A parallel circuit, parallel circuits, we should say plural, are multiple, which could be 2, multiple loops running side by side, hence parallel, side by side. So let's draw. Now this time I'm going to put just 1 battery, then I'm going to put a switch right here, then I'm going to put a light. So far all I have is a series circuit. But now I'm going to put another light bulb right here. And notice that light is parallel to this one. It's another loop, it's just running beside that loop. And then I'm going to put another loop over here. I know it's going to go behind my picture, but you can still see it. Oh, I made it fit. Well, now think about what this switch is going to do. That switch is going to turn off everything. But now think about, because if it can't make it through there, then it can't make it through that light, it can't make it through that light, it can't make it through that light. Well, now let's put a switch, and I'm just going to draw it like that. If we put a switch there and close everything else, that switch is going to control, this switch would control light A. Because if it can't make it through there, it can't make it through the light, but can it still go through B and C? Yes. B and C would stay on, A would turn off. Now let's put a switch here. What's going to turn off? If we put a switch there, A will stay on, B and C will turn off. What if I put a switch here? Turns off B, but A and B stay on. Every switch is closed except for the one that I'm drawing. So we are closing those switches, or they don't even exist. But now I'm putting a switch there. It's going to turn off B. What if I put a switch here? It's going to turn off C. And I might draw it here, but I could put it over here. Any switch between that spot and that spot, anything that goes between those 2 dots is going to turn C on and off. We are going to build circuits in class and give you a lot more hands-on experience, but please have these notes ready so you can go back to them, because these notes are going to be vital for understanding electricity and understanding how to do our shoebox project. I will be handing out this worksheet. It is, I believe, 11 descriptions using cell, parallel, series, switch, open, closed, and then we have 11 pictures. You need to match the picture to the kind of circuit that is being described. Thank you very much, and I will see you in class.